Hey guys, Mr. Bowman here. Today's video, we got our learning objective in red. We are learning to model bridges with certain graphs. And I've got three bridges set up on the left, and we're going to try have a go at using features of the bridge with features of our graph to come up with a mathematical graphical model to represent those bridges. So the first one, this is a local bridge. Hopefully many of us have driven through it. And we can kind of see in the graph below that it does look a bit like a parabola. And what we're going to do is, we do need to state it, but we're going to assume the white part of our bridge, just in this area here, we're going to assume that intercepts the origin at 0, 0, which means we've got an x-intercept there. So I'm just going to write 0, 0. So we've got a point there. We're also going to assume the end of the bridge, which is 60 meters long, will be the next intercept. So that would be 60, 0. So we've got those 2 points. Just going to zoom that out so it looks a bit better. So we've got some x-intercepts. And the other thing we have information on is we do have information on the vertex as well. We know it has a height of 22. And we know that vertex should be in the 30 meter mark or the middle. So 30, 22. There you go. So this here's our bridge. So what I'm going to do is I'm just going to scale down the top or the y-axis just so it looks a bit more representative of what we're going to do. So I've done that now. So we've got 3 points. It does look like a parabola. So we now need to come up with a graphical model that helps us represent that. So I'm thinking, so it's got symmetry, which is a parabola. It's got a vertex. Looks like we've got 2 x-intercepts. It's looking really good for a parabola. Okay, so let's look at our vertex or our x-intercept form. So y is going to be equal to a, which we don't know, but we do know the brackets. They're going to be x because it goes through 0, and x minus 60 because it goes through the intercepts. It's also upside down, which is going to make it negative. But the only thing is we do need to somehow figure out how to get that to the peak of 22. And here we're probably going to do a bit of trial and error, or we can do a bit of algebra to help us as well. Okay guys, I've switched screens and I've got the beginning of the formula that we've developed, and I've also got a coordinate that we are aware of. So we're going to substitute those values in. So we know y is going to be equal to 22. 22 times a times 30 times 30 minus 60. That's going to become 22 is equal to a times 30 times negative 30. So 22 is going to be equal to a times negative 900. A is therefore going to be negative 22 over 900. And that means the equation of the parabola that we're looking at to model our graph, negative 22 over 900. We can simplify that fraction if we want to, times x, x minus 60. So let's put that in. I'm going to pause the video. Let's put that back into Desmos to see if that equation hits the vertex that we are looking at. Okay, we're back into Desmos. We said it was going to be 22 over 900. And if you have a look, spot on, that hits exactly the coordinate that we're looking for. And if you look at the graph and the features, both of them are pretty symmetrical. And both of them meet the criteria, starting at 0 and having a width of 60. So that looks really good. If you wanted to account for the height, maybe above the water, so let's say this bridge is 10 meters above the water, maybe you can add 10 to lift that bridge, and the bridge starting and finishing at the 10 meter mark. So the road level would be y equals 10. And we can see our parabola matching that at the intercepts of 0 and 60 as well. And if you're not sure as to the height of that, what you could always do is mathematically you could generalize your formula. So we don't know the height. We could just say plus h being the unknown variable of height, which would shift it up however high the bridge is off the water. But we'll assume it's 10. So hopefully that made sense, and we did a bit of a generalization as well. Our next bridge, we've got the London Tower, and I'm just going to make up some numbers just to support our case. So the end of this tower, we're going to assume that that's 10 meters off the ground. And at its highest point, we're going to assume that is 80 meters. And we're going to try to model this portion of our, or of the London Tower. So what I'm going to do is I'm going to assume this bit here, that's the y-intercept. So we know the y-intercept is going to be at the 80-meter mark. And the other thing we probably need to assume is how long it is. Let's say that's going to be 100 meters as well. So let's put in the points that we are aware of. So we know the y-intercept, well, that's going to be 0,80. We are, so that's now on our graph. And I'm just going to adjust the scale of my x-axis so everything fits in. There we go. So it's 80. And we also know this point here, well, that should be 10 point. So x is 100 and y is 10. So we do know those 2 points. So this graph, it's a bit of a weird one. We could model it through a number of graphs. It could be a hyperbola or hyperbola. Could be a decay exponential graph. But what I'm going to do is, for me, that looks like a hyperbole or hyperbola the most. So I always have issues pronouncing that. And we're going to have a go at modeling a hyperbola with that. And what I am going to be doing is I am going to be assuming a few things. I am going to be assuming that there are asymptotes running across that. So that looks like maybe that's x equals 5 meters maybe. Or -5 in our case, because it's after the y-intercept. And maybe here, maybe that's y equals 5. So I'm just going to draw those in. So I'm just going to assume a couple of things. So assuming there's asymptote at y equals 5, and assuming there's an asymptote at x equals -5. So we can see those asymptotes gone in. And if you have a look, that does look pretty reasonable. So we now need to see, can we get that? So at this point here, which is at 5, -5, that tells us about how much it's been moved up or down. So let's say that. So our default one is 1 divided by x. And those asymptotes, they've been moved up 5. So that's our C value. And they've been moved to the left 5, which is the opposite. So it looks like our asymptotes are now in line. The only thing is, we've got no clue about these points. So it clearly doesn't go into those points. And what that does mean is, that does mean these numbers, or the number at the top, will be a lot bigger. So we need to figure out a value which satisfies this criteria. So what we're going to do is I'm going to pause the video. We're going to switch back to OneNote or to PowerPoint, and we'll try to come up with an A value. We may not be able to find one that's perfect for both, but we do need to find a relatively good fit for this graph. Okay, guys, so we're on our London Bridge example, and I've got the formula that we came up with. 1 divided by x plus 5, and then we're going to add 5 to that. That was based on the asymptotes, and I've also written down a point on the x-intercept, the y-intercept, and that was 0,80. So at that point there, x will be 0 and y will be 80. We're going to substitute those into our equation to try come up with an approximate a value, which would be up the top. So y, 80, is equal to a divided by 0 plus 5, which comes to 5, plus 5. So that makes 75 is equal to a divided by 5. So a is going to be 75 times 5. And that comes to 150, 200, 300, 375, hopefully. Okay, just double check. So that 375 was correct. And that means y is going to be equal to 375 divided by x plus 5. And we're going to add 5 to that as well. So we do have a model that will definitely go through our y-intercept, but we may have issues with our lower number, but we'll see how that goes. So I'm going to pause the video, flip back to Desmos. Okay, we are back on Desmos, And as noted, we did calculate A to be 375. And as predicted, it doesn't quite hit that bottom number, but still relatively happy with it. It is quite close there. So we do appear to be about 1.5 meters off. But generally, so it's not perfect, but generally what this equation does is this model does model the Tower of London.